All right, we're going to take our exploration and expand it a little bit more and start looking at exponential functions numerically. And this will help deepen our concept of how exponential functions are behaving and what they do. So first, let's take a look at a linear function. So we know how this works numerically. We plug in -2, we get -4, -1 times 2, 0 times 2, 1 times 2, 2 times 2, and 3 times 2. And what I want you to notice is the slope. Now we know about the slope. It's the rate of change. And on linear functions, it will be constant. And we, of course, are seeing that x goes 1, y adds 2. And I've got to this point, now I add 2 again. So let's redo that. So now I'm going to add 2 again. And then go over 1, add 2 again. And so we actually see that numerically as well. We're looking at the tables, and each time x moves 1, we're adding 2. And then x moves from 0 to 1, we add another 2. And we add another 2. And we add another 2. So starting at the beginning, -2, x goes to -1, but the y's get 2 bigger. So there's that constant rate of change. A delta y is a constant. So we've got this change of 2 each time. Delta y equals 2. Now let's compare that to the exponential function. So a couple of quick reminders about exponentials. We were going to evaluate. Let's start off with one of the really important ones in the middle. 2 to the 0 power. So when x is 0, I plug in 0. 2 to the 0 power is 1. And what about the negative powers? Well, I'm hoping you're remembering that that is a reciprocal. So we get 1/4. And then, of course, 2 to the -1 is reciprocal. 1 over 2 to the 1 power, which is 1/2. And then 2 to the 1, 2 to the 2, and 2 cubed. Those are pretty standard exponents. So we're going to get 2, 4, and 2 to the 3rd power is 2 times 2 times 2, which is 8. And all of that's graph for us. Here at -2, y is only a quarter way up. -1, y is only halfway up. And when y is 0, nope, I'm saying that wrong. When x is -2, y is a quarter up. X is -1, y is a quarter up. X is 0, y is 1. X is 1, y is 2, 4. And then when x is 3, y is way up here at 8. Now I want to explore the change and look at the change. It doesn't have a constant rate of change like a slope does, but there is something that is consistent about how it changes. So when x moves 1, I add 1. When x moves another 1 this time, we added 2. When x moves 1, we're going to add 4. Okay, so the rate of change we can see is not constant. It went up 1, it went up 2, it went up 4. But there is a pattern here. Going over 1, up 1/2. And then I went up 1, then I went up 2, and then I went up 4. And I'm trying to think about, okay, it's not the same number of change every time, but mathematically what's happening? Is there a mathematical prediction that you can use to predict mathematically what's going to happen on this next one? Well, if we look at 1 to 2, it did add 1, but it's not adding 1. for the next change. So the pattern doesn't have to do with adding. So mathematically, I got to think of another option here. And a half, 1, 2, 4th, I hope you kind of see it, and especially because it involves an exponential. There's a lot of multiplication going on here. And so if we consider multiplying 1 times 2, I'm going to make a star for multiply. 1 times 2 makes 2. Does that pattern continue itself? Well, what's 2 times 2? That's 4. What is 4 times 2? That's 8. So if we keep this pattern going, and we took 8 times 2, we'd be getting 16, which is the next one. And that's, of course, what happens with 2 to the 4th. So there is a constant pattern here. But the pattern is not by adding. So it's a pattern of multiplying by 2. So we do have a constant change. But the exponential equation comes by a constant change of multiplying. Whereas the linear function has a constant change, but it comes by adding each time. So that's the big difference between exponential functions and linear functions. So the idea of the multiplication each time is what changes and causes the exponential function to grow.